second day. It's just a couple of announcements, but before let me introduce Mark Moll. It's very few people in this community in the world who know about motion planning like Mark does, and especially integrating task and motion planning. Very important area, at least in our opinion, for the future development of planning within the field of robotics, and perhaps vice versa. So Mark from Rice University will talk to us about this today. Welcome. Thank you again for coming. By the way, Mark is also leading the effort in developing the open motion planning library right at MTS. This is an important piece of software for any of you who have ever used any motion planning stuff that's for example, built into ROS. I think your tools are used there, so we're very lucky to have. Just a couple of announcements. Yesterday's slides, I have sent to you the stuff from Patrick, and I've received UC slides. I will also send them to you by email, but Mark has his own repository of material which he'll talk to you about. So, thank you.
Thank you. I'm very honored and privileged to be here. I keep myself mostly still in sort of robotics land, but I'll present my view of how motion planning and task planning can be integrated and hopefully help in sort of bringing the AI and robotics communities closer together. Over time, sort of robotics has sort of drifted one way, and AI has sort of drifted another way. And now, in the last couple of years, there's sort of an effort to bring these communities back together. And one natural point of connection is task and motion planning. And that's what I'll be talking about. So I have a web page with a few pointers, and I'll further sort of study after the summer school's over. It also contains a copy of all the slides. So you don't have to look at it now, it's not necessary for summer school, but just write it down somewhere. Okay. So, did everybody hear me okay from the back? Can somebody raise their hand if they have trouble or yeah? Good? Yeah. Okay. So this is a picture of Rice campus. If you guys are ever in the Houston area, please let me know and come visit us. It's a beautiful place to visit. Always looking for good students too, if you're considering our postdocs. Right, let's get started. So, let's say I'll just present a motivational example for why we want to combine task and motion planning. So let's say we have some domestic service robot working in some kitchen scenario, and we want to clean up the dishes. We just put them in the dishwasher, and eventually once they're clean, put them up somewhere in cupboards. And maybe our task planner gives us a couple of plans, and maybe we have some preferences on how that should be organized. And at the same time, there's complex motions involved to avoid all the obstacles. So it's not something that we can only solve with task planning, and not something that we can only solve with motion planning, because there are maybe higher level constraints, and there's different orderings of the task that is better left to task planning. Right, so we really have to worry about both motion and task planning. And there are lots of ways to sort of view this problem, right? So I showed a picture to typical AI community, yeah, that's task planning, right? And then you show this to a robotics person and say, well, yeah, that looks like motion planning. Really, but there are just different views in the same area. And different communities have been looking at this from various points of view, right? So you can really consider this a controls problem, or a learning problem, or a motion planning problem, and so on. But we have to reason over task, and we have to reason over dynamics. Well, maybe we don't really want to worry about dynamics, we just simplify things as a geometric problem. But in some sense, you are sort of still reasoning over dynamics, you just have made some simplifying assumptions that you say, well, we can just reduce this to a geometric problem. Alright, so let's start with the motion planning. So in the classical setting, we just have some start state of our system. Goal state, and all we want is a path from start to goal without any collisions and while satisfying any constraints. So for this car-like system, we might require that it has car-like dynamics, so it satisfies the differential constraints of car motion. So robot motion planning is typically done in a continuous world with constrained motions. Right? So we don't have a discrete cert, we can't enumerate all possible states. So So it's a very different flavor of problem compared to most other problems we do science, right? It's a kind of search problem, and now it's in a continuous space. So we need to know something about the robot and its geometry, and the same goes for the environment. And we also may need to know something about the robot's physics and the world physics. And there can be various degrees of detail there, right? And for this to be useful, we need it to be accurate and predictive. Right? So we need to capture enough details about the world and the robot such that when we execute this plan, that it has a reasonably high chance of succeeding. So if you have a really powerful motion planning that models everything in the world and everything about the robot, then you can simplify the task plan. But if you go that route, then of course motion planning itself becomes really, really difficult. Right? Really, if you're trying to model every little aspect of the motor of a robot and slippage of the wheels and everything involved in the physical world, you make the planning problem, motion planning problem, much, much harder. So we need to find the right balance between how much you want to solve in motion planning and how much you want to basically rely on control and how much you want to leave to the task planner. You can really think of it at the highest level as the task planner. You delegate some work to the motion planner, and the motion planner then delegates some work to the controller. So in practice, we don't really solve a problem and we're done forever. Typically, we are running this in sort of replanning. So the classical view, there is sort of a sense plan active. We observe the world, we plan our current understanding of the world, and then we execute that plan. In this case, we have a partial model of the world, the black obstacles, and the gray parts are sort of unknown. There might be doors that were assumed to be open, but they turn out to be closed. Again. So this is a car-like robot over here that's planning possible trajectories for the next time step. And remember, this circle indicates the sensing radius, so you can sort of see through walls. Let's not worry about that, but we can sort of figure out that some doors are closed when it gets close enough, and we'll find an alternate plan. So it keeps going until eventually we just go over there. So that's I won't be talking a lot about replanning, but just keep that in the back of your mind that typically we have to do this reasonably quickly because we are expected that the world changes around us all the time. You can't just, well, in some settings you can plan once and be done with it. If you're planning for, let's say, a group of robots in the traditional assembly line, the assembly line might not change for a while, and then maybe you can get away with planning once and solve problems forever. Now, here's a slide with all the bad news about motion planning. So in the late 70s, early 80s, people were very focused on implementing or finding exact algorithms and analyzing the complexity of robot motion planning. Turns out that only the easiest versions are still polynomial time. So if you have just 3D translation, it's called the sofa mover problem, where you just have a 3D rigid body, and we're only allowed to translate it. That problem is solvable in n order n to power 2 plus epsilon. But if you add rotation to it, it's still polynomial, but kind of bad. It's really difficult to implement. And then when you go to more general problems, n degrees of freedom, where you have, let's say, n joints or in a robot and add rotations, the problem becomes p-space complete. So that's very bad news, because it really means that if you want to solve things efficiently, especially in the replanning loop, it seems that there's no hope, right? Part of this, the reason that it becomes really complex is that, well, I'll talk about that later. When we introduce dynamic constraints, it gets even worse. In some cases, it's not even undecidable. We have nonlinear dynamics. You take a car as a sort of example where you have nonlinear dynamics. Even the simplest car model where we just have boundary curvature paths, and it's sort of undecidable. And then if you have hybrid systems, well, I don't know, probably undecidable. In hybrid systems, it's a car with gears, with shifting. For instance, that's a sort of a hybrid system. It's definitely undecidable. So at that point, we were sort of, well, what do we do now? Right? It's p-space complete, but we still need to solve motion planning. There were algorithms, but they turned out to be very impractical to actually implement. So then the next thing is, well, the exact algorithm is just sort of impractical. What next can we do? Well, we can discretize the world in the number of cells, just try to just do a discrete search from cell to cell, and make all kinds of simplifying assumptions. It kind of works, but it does not scale easily to higher dimensions. So if you have a robot with lots of degrees of freedom, then that means that you have to have a cell decomposition in very high dimensional space, and how you should pick this grid is not so clear, and you get exponentially many cells. It doesn't scale very well. Another approach could be to just do a purely reactive control-based approach. It's online, very robust to disturbances. You need to have some good reference trajectory, so you're kind of pushing your problem somewhere else, and you still need to actually find the initial trajectory. Another approach that has been tried for a while was potential fields, where we basically say, well, let's say we pretend that there is a hilly landscape in the space that we're planning in, where we're at the top of the hill at the start, and we're at the bottom of the hill towards the goal, and we're trying to sort of follow a gradient, some sort of distance to the goal function, and we just hope for the best. Needless to say, you can either get stuck, you have obstacles in your environment, and you need some strategy to get out of these local minima if you're following a gradient. And that turns out to be difficult too. But that idea of using potential fields and basically trying to figure out how we can get unstuck led to the development of the sampling-based plans, which is something that I'll be talking about. So there, it turns out that you don't actually need that sort of gradient, but the strategies that people came up with in potential fields to get unstuck led to the development of sampling-based plans. So they're very fast in practice. It turns out that even though we have this worst-case complexity, that doesn't change. It turns out that many problems in the real world don't exhibit that worst-case behavior, and we can get very good performance with sampling-based plans. However, they're not without problems either. In this case, we cannot recognize that the solution may not exist. So again, we just keep running forever, and we just think that the problem is really hard, whereas there might not be a solution at all. And we can't distinguish these two scenarios. So that's an important drawback. Okay, so now I've explained what motion planning is and so where we are today. So sampling-based planners are not the only way to do motion planning, but it is a very common and popular flavor of algorithms that is used these days for robots with many degrees of freedom. So that's what I'll focus on. It's also the area that we're working in, so I can say something with more authority about that than other techniques. So I'll give an overview of sampling-based motion planning. Then I'll continue with how we can integrate task planning with sampling-based motion planning. At that point, this may take us a little bit past the coffee break, maybe we're ending right at the coffee break. And then afterwards, I'll give an overview of the Open Motion Planning Library, a piece of software developed in our group that contains many popular algorithms, some developed by us, some developed by others. And I'll do a little show and tell of how you model problems and how you solve problems with this library. Okay. Right, so let's start with the overview of sampling-based robot motion planning. Okay, so I first have to define a number of concepts that are necessary to really talk about these algorithms. So we have a workspace, which is one type of space. Then we have the description of a robot, which will lead to the state space, which is the space that we're actually planning in. And so there's some mapping between state space and workspace. And I'll define what a path is, what we mean by a planning instance, and how we sort of define a particular instance of a motion planning problem. Okay, so the workspace is really just the environment that the robot operates in. We have a certain geometric description. So for the purpose of this talk, we'll just assume that we have a static environment, right? No dynamic obstacles, nothing is moving around, just have a static environment and a geometric description of it. And we have a boundary of this workspace in terms of the obstacles. Then for the robot, similarly, we have a geometric description of this robot, but we also have a parameterization of its degrees of freedom. So degrees of freedom are really just joints in most cases. So that's if you have a mobile manipulator, it can drive around in the plane, so it can translate and rotate the plane, and maybe it has arms, so it has joints, elbow joint, shoulder joint, and so on. All of these parameters, once I know these parameters, and I have a geometric model of every part of the robot, then I know exactly where the robot is in space. That's what you can think of the vector of the parameters that the degrees of freedom as a point in space that uniquely describes where the robot is. So that's then the state space. And so we have this, let's say we have a 6 degree of freedom robot. If I know these 6 parameters and I have this geometric description of the robot, then I know from those 6 parameters I can construct the geometric pose of the robot anywhere in space. Right? So we call it the state of the robot, and we're searching in this state space for paths. Now, so in this state space, we may have some bounds in it, and so we have this space that we're searching in. Some states are in collision, the states are collision free. That's where we're mostly interested, of course, in the free space. So we call that's basically the part of the space that is where the robot is not colliding with anything. So finding this free space is very difficult. We can't easily describe the set of collision-free configurations and the ones that are in collision. If that were easy, then essentially we would be done. That's the main difficulty in motion planning. That based on this parameterization of the robot, you get a very complex space or a complex boundary surface between the configuration in collision and the ones that are not in collision. The algebraic complexity of that surface makes it so that motion planning in the general form, the geometric version is p-space hard. So that's where the complexity is coming from. Mapping the parameter space to the workspace and computing the boundary between the free space and obstacles determines the complexity. Okay, so then a path is simply a function that maps the range 0 to L to S3. Right? It creates a continuous curve in S3. At 0, we're at the start. At length L, we're at reach our destination. And we just have a mapping that says, this is the pose of the robot everywhere along the path. And every point along that path is continuous. This is eventually what we want. Now, the planning instance is basically given a robot, and given a workspace, and given constraints on the motion. Let's say we don't want a path that's too long, or we want a path that's very smooth. So those are some additional constraints you can add on to the motion planning model. What is now a path that satisfies the model? So this is the planning instance. Given this, we want to solve given two specific states. What's a valid path that satisfies all the constraints and connects start to goal? Does that description make sense? Everybody still listening? Alright, so now we can talk about how we can actually solve that particular problem. And this is really one basic version of the problem, and we'll look at many flavors of this. This is the most the canonical version. One start state, one goal state, going on to find a curve that connects them that lies entirely in free space. Alright, so the first sampling-based algorithm that was proposed was in 96. Well, this is the general version, the conference version a year or so earlier. It's called the probabilistic roadmap method. So the idea is very simple, and actually, of course, there's a very nice intuition behind it. If I want to direct somebody from, say, my office right here to somewhere on this map, then I really just describe a series of waypoints. Just like go from here to here to here. I don't really give this complete continuous mapping. It's sufficient to just map out the environment with waypoints and to say how you can get between waypoints. It's sort of a simplified representation. So in general, we don't really know where to pick those waypoints, so we're going to use random sampling. And we have a simple local planner, it's just a straight line that we'll use to sort of connect different points. And we'll build up a map of the space. So where can we go, what's accessible, and how do we get to other nearby waypoints. So we're going to start with a very, very basic version of the problem where we just have a point robot in 2D. So not a very realistic robot, but it's a point that can just translate and translate freely. A very simple example, so I emphasize that this is not how we'll do things. But from this illustrative example, we'll see that actually we can use the exact same approach in much more complicated cases as well. So once we understand the basic idea of 2D, we'll isolate what techniques that we use and how can we generalize this to higher dimensions. Okay, so let's say this rectangle is our free space. We have these obstacles in here, and we have our point robot. Now, the first thing we're going to do to map out this area is sample a bunch of states. Each dot is a robot state. We'll just sample at random. Now, we can just look at pairs of states, do a straight line correlation between them, and say, well, let's see if that's collision free, and if so, we'll keep that second. And we get this sort of graph-like structure, and we keep going, keep adding, testing more pairs of states, until eventually we get some graph that its connectivity approximates the connectivity of the free space, the underlying continuous free space. And so it's a simplified description of this continuous space. We're going from a 2D continuous space to a 1D graph structure. And now when we have either a query that says I want to go from this very specific start state to a specific goal state, what we'll do is we'll find neighbor or milestones nearby that we've sampled, nodes nearby. Say, well, can we just connect that with a straight line segment to the graph? Then we have basically our on-ramp to our roadmap. And we do the same thing where for our goal, we find for the goal states nearby that we can connect to. It'll be our off-ramp, and we do our favorite graph search algorithm to find a path in this graph, and then we extract that path in the solution for A to B. And the nice thing about it is that once we've constructed this roadmap, we can use it for any other query as well. So we get a different start goal query, we can reuse the same roadmap. We don't have to start planning from scratch all over again. Okay. So what did we do? What kind of primitives did we use? And how can we generalize this? And so the main primitive is randomly sampling states. So that seems that we can probably generalize to many other spaces. Then we use connections between states. If we have a local planner, we use straight lines in this case. Not necessary to use straight lines, but it's usually what we do. And then we have some underlying data structure that stores everything. Our actual roadmap is just a graph. And our vertices are now a subset of the free space, and we have an edge that means that we have a local planner on the path. So you may wonder, like, well, why use sampling? Why can't you just have a discrete grid over space and just say that's what we'll use? Well, one problem with the grid is that, well, you don't really know in what order to process these grid points. You really want to get a good coverage of the entire space. And if you don't really know what order to pick, maybe random ordering is just fine, and then pick random and why settle on a grid coordinates. There's always the chance that you don't find a solution because you discretize the wrong resolution. Okay, so that's one reason we use sampling. The more important reason is that it goes back to the complexity of program motion planning, is that the C-space obstacles, the state space obstacles, get extremely complicated. So here we have a robot with 2 degrees of freedom. There's this alpha angle, so the shoulder joint, and we have an elbow joint over here, and there's this circular obstacle over here. And the robot is attached to this point. But this, let's pretend that this is not an obstacle. The arm can just fling around everywhere, there's no joint limits, but this thing forms an obstacle. Now if you look at what that obstacle looks like, if you sample all possible angles, so here we have the axis for alpha, here the axis for beta, you look at all combinations of alpha and beta, and which combinations lead to a robot state as a collision. You get this sort of funny looking shape, and it's clear that the straight line path from A to B is not feasible. If you interpolate a straight line in this space, it's not a straight line in this other space. Right? If you do this straight line motions with your joint space, it corresponds to these arcs and more complex curves in theoretical space. That path is definitely not possible. Doesn't mean that you cannot go from A to B. It just means that this space also kind of wraps around. That if we are allowed to sort of go off the side of this side and then enter the space in this side, then you can go back. You can rotate the arm around the other way. So there is a solution in this case. So topology is sort of another way that things get messy. Right? We have a torus here and just unfold and make it flat. So in 3D, things get even worse. Most arms have more than 2 degrees of freedom. You usually have 5 or 6, and you have a hand attached to get the force. So you have lots of degrees of freedom typically. So 3 is still really not that many. As you can see that if you have just one hole in the way, this is sort of a side view, this is a top view of this arm. The configuration space obstacle will get really messy. And this very non-smooth surface is just an artifact that we sort of did this at a discrete resolution. This is not how it actually look, but it's an approximation that still captures most of the complexity of what this boundary of this obstacle would look like in the state space. So it's messy, and we'd rather not compute this because it get only worse when you add more and more dimensions. Remember, this is only one really simple obstacle, and let's see how complex it gets. So you can only imagine that you have complex geometric obstacles and more degrees of freedom. This gets really, really bad. So this is why sampling is helpful, because we don't necessarily want to find the path that lies on the boundary of free space and obstacles. We just want to find a feasible solution that is entirely in free space. And if you can avoid the boundary exactly, which turns out you don't really need, then you can save all the time. Okay, so it sounds like, well, yes, maybe, but in extreme cases, or in the worst case, of course, we have these cases where the boundary is exactly where we need to be, because that's the only way we can go from A to B. If you have a very narrow passage between obstacles, then this really matters. Right? Because sampling really doesn't change the complexity, it just turns out that in most cases, you don't have these corner cases where we really are epsilon away from all the obstacles all the time. You usually can get away with sampling. But we haven't changed the complexity of the problem. Just want to make sure that we understand that sampling is great, it works well in many cases, but it's not changing the complexity of the problem. So, and we can do this very efficiently. Let's say keeping this graph structure around is very easy, very nice compact structure, and compared to keeping analytical descriptions of the boundaries of these obstacles in the free space, that's very hard. Okay, so now the other method we use besides sampling is connecting samples. Typically we use straight lines in the state space, and you just check to see if it's valid. So the local planner is allowed to fail. It's usually something that's simple, it's fast, something that you can call repeatedly on different pairs of states, and it will either say yes, the path exists, or it will fail, and you know a path might exist between those points. And you just have to try different directions. So even if the path might exist between two nearby states, but maybe the straight line path is not the right solution. Then you have to find something else. But eventually, through sampling, we will find something else. We'll just try to go from A to B via some other intermediate point. Okay, so the reason that sampling works well in practice is that collision checking can be done really, really efficiently. So in computational geometry, people have come up with all kinds of clever algorithms that use bounding volume hierarchies and geometric primitives that you need to test whether two obstacles or two geometric objects are penetrating or not penetrating is actually can be done reasonably efficiently. So for any particular state, you can test quickly whether it's a collision. And that's what allows us to do sampling. So when we sample a particular path, we can basically want to make sure that every point along the path is collision-free, but we don't want to sample infinitely many points along that path. So we typically discretize that path at some resolution, and then we can use bounds on clearance to predict what will happen in the intermediate points. Okay, so we can still give an overall certificate that says, yes, this whole segment is collision-free, even though we checked only a discrete number of points. So there's some bounds that you can use in the process that will allow you to sort of skip over some small segments. Okay, so let's go back to PRM, obviously Grover method, and see if we can generalize it now. So I've drawn here this 2D landscape, but in reality, we don't know these obstacles. That's exactly what we're sampling. All we have is we have the sampling random points. Sometimes we get bad samples, so we just check these samples with our collision checker, or whatever other function we have to check for stability. And some samples may be bad, and some samples are good. Obviously, we keep the good ones, throw the bad ones away. And same thing for these edges. We pretend to be know these obstacles and draw edges between them when the straight line segment is clear, but in reality, when we are using our local planner may not do straight line manipulation, they do something else. And what a straight line really means depends on which space you're looking at it. So we might as well just draw them in little squiggles. And some squiggles are valid, some squiggles are not. And really, everything else remains the same. We don't know as much as the picture seems to suggest. We just really have sometimes there's a squiggle that works, sometimes there's a squiggle that doesn't work. We don't know. We don't care really what it exactly looks like. And we have bad samples, good samples. And eventually, we just draw this graph embedding with dotted lines. Really, there are no straight lines. But it's a concise representation of all the motions that are possible. And a dotted line really doesn't mean that we have to follow exactly this path. It just says our local planner found a path that may not look exactly like this, but there exists a collision-free path between here and here. That's all it says. That's a really nice, concise representation of how to get anywhere in space with this graph. Okay, so we don't actually see these obstacles. We see this. Okay, so you may wonder, well, how do we know when you're done? Right? Well, we don't. That's kind of the main drawback that I alluded to earlier. Keep sampling and sampling, but we don't know since we can't really see where the exact boundary of these state space obstacles. We don't know exactly if we just were very unlucky in picking certain samples, or if we just need to keep going in a better and better approximation. So if a path exists, we may not always find it. And it's the kind of completeness guarantees that you can give is that it's probabilistically complete. And I'll make that a little bit more precise. So it's kind of an important property. So it sounds like, well, what does the algorithm give you, right? It may not work all the time. And what good algorithm is that? It turns out that yes, it actually will work all the time when you give it enough samples, and the probability of failure goes down as you add more and more samples. And we actually give you a rate of convergence. And it's a little bit tricky to give you a whole proof, so I'll give you just a little bit of intuition. So let's say we're relying on some geometric properties of the space. So imagine that this blue dot is this state in our space, and this yellow region is the part of the space that it can see. So this point can see basically with a straight line view all the yellow area, and same over here. And the fraction of the space you can see is parameterized with epsilon. So this is a very open space, we have a very large epsilon, this is a very sort of constrained space, but we have a sort of narrow passage. This point can see much less. But for the whole space, maybe we can find a lower bound of epsilon. That says something about how hard it is to plan in this space. So let's not worry about how we compute this epsilon. Let's say that there exists such a number. And let's say we, given our planner a probability of failure, that we want to find a solution if one exists with probability 0.99, and we have a probability of failure of 0.1. Then you can say, well, then the number of samples we need is approximately equal to this formula over here. So there exists a formula that says, well, if you happen to know what the visibility of each point is in the worst case, and you have a probability of failure, then you can say, this is how many samples you need. You can show something like that. And from this, we can sort of turn this around and say, well, as we can keep adding more and more samples, the probability of failure goes down exponentially. So that's not all bad news, right? So it just says that if we, even though we don't know exactly what this number n is, as we keep adding more and more samples, the probability of failure goes down to 0 at an exponential rate. Essentially, this corresponds to the eventually we start putting sort of a suspected, especially if there's one plan, you can sort of put balls around it and say each ball can see this much of the space, so every ball can see every point around that path, and eventually you can sort of show that the probability that we have these balls, that we have a sample of each of these balls is some number. So there's a way that you can sort of, with probabilistic analysis, show that this is how this proof works. And this is just with the simplest possible sampling. It doesn't assume too much. Okay, so let's go back to these primitive techniques. This clock is not right.
Clock is wrong, and it's been slow for 2 days.
Okay, so we have select the sample. Usually we do uniform. We'd like to do a little bit better. We'd like to say, well, if we have a wide open space, maybe we don't need to cover that uniformly. A few samples is enough there. But if we have a windy passage that's very narrow, then we probably need more samples there. And this is kind of tricky because you're exactly right. Connection is the other parameter. Who do you connect to? Generally, maybe you can try to connect to all samples that you've found so far. Of course, that's not very efficient. We want to just connect to some nearby neighbors. How you connect is also sort of open, because we can typically use a straight line plan. Then you have to store all of this in the roadmap. We can just use a graph. Alright, so let's start with selecting the sample. So people have come up with very different techniques. So one idea is to use Gaussian sampling. It's not exactly the Gaussian way of thinking of it. The idea is that you sample one point uniformly at random, and then you sample the second point from a Gaussian around it, small tight Gaussian. And then if one is collision-free and one is in collision, then you keep the ones that's collision-free. If both are in collision, then you throw them all away. If both are in collision-free, you also throw them away. So what it ends up doing is that you end up with these samples that are along the boundary or in these narrow passages. And remember, any straight line path, can cross all this empty space. And we don't really need that many samples here, right? If we have a roadmap where a start point is somewhere here, then we can connect all of these points with a straight line path. So it really doesn't make sense to fill this with samples like it's done over here. So this is what you get with uniform sampling. This is what you get with Gaussian sampling. So many fewer samples. And you still get sort of the right density of sample in the narrow passage. So that's one idea that seems to work reasonably well. Then there are other ideas on trying to sample the medial axis, which is basically this, the set of points that are equidistant from pairs of obstacles, or more multiple obstacles in higher dimensions. And various other heuristics that you can use to sort of guide the selection of points towards the parts of the space that are difficult. So in the end, this may seem like a contrived example where you have lots of open space and one narrow passage, but that really is determining the complexity of the motion planning problem, this narrow passage. So So when people talk about the narrow passage problem, what they really mean is just the motion planning problem. Because if you can solve that efficiently, then you can solve everything else efficiently. You spend exponentially more time on it, and basically finding a path through here than anywhere else. So it really dominates the planning cost. So that's why people have spent so much time developing all kinds of heuristics to improve the odds of getting samples in here. Just because that's all that matters. Alright, so now let's go back to connection. Like I said, we don't really want to connect all to all. We have to have some sort of neighbor structure. That says, well, we have to have a way to find nearest neighbors. This is another thing that can be very expensive, especially if you go to higher dimensions. So if you have a Euclidean space, you can use these KD trees, which is a nice partition of the space. So the axis aligns partition where you can efficiently find near neighbors. If you have rotations, for instance, that doesn't work. And if you have rotational joints, which a lot of robots have, then KD trees don't work. And you need something else. It also turns out that computing these exact nearest neighbors becomes very expensive in high density spaces. But oftentimes you don't really need exact. Maybe approximate is fine. Right? We have this local planner that's a lot of the field, and we just want to have a reasonably densely connected graph. Actually, it doesn't even need to be that dense. We just want to have a connected graph. Right? So we can afford to make some mistakes. These approximate nearest neighbor methods give you bounds on how many true neighbors you get and how many are a little further away from the true nearest neighbors. So that's actually the reasonable strategy. Another thing you can do is, well, we only want to add connections to states that are not part of the same connected component. So we're trying to create a tree structure rather than a dense graph. The reason that you might want to do this is that evaluating whether an edge is collision-free takes time. If you can avoid doing that, then you get to the path much sooner. Right? Because you avoid computing all these things that are already connected to another path. And so that's, of course, the downside is that the kind of path you get if you're doing this, if you only add edges that are to a different component, you get very winding paths, right? Because you have very few options to go from A to B, but you have to use detour. Okay, and storing visually is really just a standard graph. If you want to test for connected components, of course you need an efficient way to do that. Those are the kind of things that we typically recommend ourselves. Just take a standard graph library and have it taken care of that. Okay, so the roadmap method described is a general algorithm. It's pre-processes an entire environment. But if you say, I only want to find a path from here to the door, and I really need a roadmap for entire King's College, maybe I can save some time. Right? I can just plan a tree of motions starting from my current position, and I try to find a way out of this room. So we start with the same setup, and we'll see that we use the same primitives over and over again. Okay, so we're going to grow a tree starting from a specific state, and typically what we'll do is we'll select one node, one leaf node, or one node in our tree, and expand an edge. So we just pick one of these nodes and we say, well, let's move in a random direction and walk down a new node. And there's different heuristics that will sort of guide the selection of the node in the tree, and different heuristics that will guide the expansion of the tree, where we go next. Because you don't really want to do a random walk if you ever sort of play around with this. If you do a random walk, it tends to more or less stay in the same place. It takes a very long time for you really to cover the whole space. So there's different heuristics to make sure that this tree doesn't stay in the same place, it really sort of moves outward to unexplored territory. Every once in a while, we'll try to say, well, let's, instead of moving in a random direction, let's go straight for the goal and see if that works. In this case, it didn't work, so then we keep going until eventually we find is a node where the straight line connection to the goal does work. So this is very easy. This is actually one of the parts that really appeals to people, that if you see pseudocode for this, and think, oh yeah, I can implement this in 10 lines of code. It's really easy. And that's kind of true. It is really easy. But we're using the same primitives here. If you pop that, essentially you still have, you select some sample. Now it's a little bit more involved because we basically select a state in the tree, and then we sort of expand the tree. And in the end of the tree really is just another graph structure. Right? So the most popular version of tree-based sampling algorithm is RRT, and sometimes it's kind of confusing because people come up with their own flavor of sampling-based algorithm and they call it RRT and something. It's a lot of heuristic. I think that's kind of wrong. RRT uses is really just a specific version of a sample-based algorithm. We use a specific heuristic to guide the expansion. It's using the so-called Moll bias. It samples a random tree in the entire space, then it finds the nearest node in the tree that is close to the random state, and then it will expand from it somehow. In some cases, you just move in a straight line towards it. Sometimes, if you have, let's say, a car-like system, maybe you just apply a random control and your car drives this way, and you generate a new state. So it's this way of expanding the tree has this expansive property that it really is trying to sort of fill the whole space. And you can also come up with a bidirectional version of it that basically you grow the tree from start to goal and the tree from goal to start to make these trees meet and go back. But there are many other ways of growing the tree. So here's another way that came up around the same time, where imagine we project all the states down to a low-dimensional space, and we have an implicit grid over this space, and we just keep track of count how many states project into each cell. And we use that as a heuristic to sample or to select a particular state. So in this case, well, this picture has only one state per cell, but imagine now there's lots and lots of states and not as many cells. Then there will be sort of distribution of density. Right? And we basically want to bias the tree growth towards the cells that are in low density areas. So we pick a cell that has low density, select a sample from that cell, and then grow the tree from there on to outward. And hopefully we'll discover a new cell, which now is also low density. Then it's very easy to sort of do this kind of weighted sampling from these density estimates. And there's different versions of this too, there's bidirectional versions. So these are just two of the possible ways that you can do tree-based expansion. There's many other versions. We can take this grid, this density estimates a step further and say, well, we have a whole hierarchy of density estimates, and we can bias our density estimates towards less dense samples that are also on the frontier of what is known. Here the tree is covered by these grid cells, and the ones that are interior cells are surrounded by other grid, non-anti-grid cells, it's called as interior. The other ones are exterior, and of course you want to have an expansive search with the bodies of the exterior samples. There are all kinds of tricky heuristics that you can use to sort of make sure that your tree expands as much as possible. There's always this exploitation trade-off, right? So maybe the solution really lies in some of these interior cells, and you really do need to sample somewhere there. So you don't want to too greedily expand outputs. You also have to have sort of a right balance between exploitation and exploration. This is something I'll come back to later. We can also use a discrete high-level search to sort of guide where we should grow our tree. So we can have a triangle decomposition, we can have a grid cell decomposition, it doesn't really matter. You first search for a collision-free path in the grid cells. You just have a representative sample for a grid cell. And then say, well, let's grow our tree restricted to this path that we found with our discrete search. I'll come back to this later, so don't worry too much if this doesn't make sense just yet. Alright, so there's all kinds of tricks that you can apply to make this tree search faster. Using a bidirectional way, you can have lazy collision checking. You which means that we generate lots of random samples, lots of different edges between near neighbors, but we only validate whether they are valid as only when we really need it, when they are considered part of our candidate solution. We validate them. At that point, we may throw out some edge to some states, and then we repeat our graph search until we find any path that is completely valid. And that tends to speed things up as well. For our ordinates with goal bias, and periodically we want to sample a path that goes straight to the goal. There's different ways to account for constrained manifolds. For instance, I have a holding a tray with two arms, with a set of valid samples where I'm holding the tray is actually level, very constrained. Sampling these kinds of robot states is very difficult. So there's different strategies for that. Of course, we can have these motion primitives. We have a car-like vehicle. You don't really want to solve parallel parking each time from scratch. So maybe you have something primitive built in that just apply that primitive and you don't have parallel parking. So all of these things can be applied and fitted in the same framework. Okay, so now let's go to dynamics. Since things get very difficult here, it's a little hard to see here, but we have sort of a weightlifter type robot, and the torques are limited on the joints, so it cannot just move the weight straight up, it has to sort of swing back and forth, and then eventually you can find this motion where the weight is lifted all the way up. These kind of motions are very difficult to find. In some cases you can find them with control theory, but in other cases really you have to do some kind of search. This sampling methods can do this. So the meta always find an optimal solution, but when a solution exists, it will find one. Here's the case. It's really impossible to see, but we have sort of car-like dynamics where we cannot satisfy the dynamic constraints, and the car flies around, flips over. In this case, we use physics simulation. And this is where we can really think of the physics or the underlying dynamics of the world as a black box. So we are given a particular random sample in our tree, and we apply some control for some duration of time, and we find our new state. And we just run this through a physics simulator or an integrator for a system of differential equations. We just get our new state. We really don't need to know anything about what's happening in this black box. Right? We can have changing contact modes, we can have slipping or rolling. We don't care. We don't really need to know all the details. We just treat it as a black box, and our pathfinder will still able to find a time that will take the robot where it to be. So we're given our initial state, and typically we cannot move exactly to one goal state. We say, well, there's a goal region, a small area in the state space. And we want to find a sequence of controls such that when we repeatedly apply the UI to QI, then we get the next state, and eventually we reach the goal once we apply this control. If we apply the sequence of controls, we eventually go start to the goal state. So it's a very different flavor now, right? It's no longer straight line connections, we just sample random controls that really might be the wiggly paths that we saw before. So it makes things very difficult to plan the dynamics because we don't really know which states are near now. If you have a car and you have to move forward 1 centimeter, it's very easy. If you have to move sideways 1 centimeter, it's much harder. If you use the usual Euclidean distance, it seems well they're equally near, whereas your local planet will have much higher success going forward or backward rather than sideways. So the metrics don't really capture that. So finding good states to connect to becomes very difficult in cases where dynamics are important. So we don't really have a good way of efficiently planning for the system for dynamics. So if you can abstract it away, then that's a good idea because it makes planning so much easier. At the same time, if you do have to worry about dynamics, you can somehow get the right primitives from control theory that basically gives you parallel parking as a maneuver, and you can say moving sideways is not hard because I already know how to do that. And you can make your parallel parking maneuvers infinitesimally small, and you can kind of pretend to be moving sideways. Of course, you you might want to associate a higher cost to that kind of path than a path that goes straight forward. Okay, but it's the same primitive that is still applied. You still have a way to select a sample to expand from. Expanded from that sample is now selecting a random control, innovating forward, or simulating forward what happens, and storing the resulting state. But everything else remains the same. It's the same ideas. Okay, so that is everything I wanted to say about sampling-based planning. Let's move on to control-based, task promotion planning. All right. So let's zoom out a little bit and say we want to move beyond just going from A to B. What we really want is to say, tell a robot to do something useful. Well, we have this robot that's helping an office environment. We say, well, it needs to warm the plant, clean the blackboard, turn up the coffee maker, pick up the vacuum cleaner from the supply room, and vacuum the orange room, and dust the stable. We just wanted to do a number of things. In this case, maybe in this exact order, or maybe in any order. And then work related, all that. Right? So it's still solving lots of motion planning problems, but it also has to figure out, well, how do I do this, or these tasks in some reasonable way. Okay, so we have a high-level task specification, we call this autonomous, or a complex mission. You autonomously want the robot to execute. You don't want to be making choices for every motion planning problem, and just do it. And we have to sort of reason over the high-level tasks, and how do we decompose this in subtasks to primitive actions, and how do we translate these primitive actions to complete motions that can be executed with a robot. And then again and again, and this sort of intersection of many different areas, so we can sort of put those apart into different pairwise intersections. So I'll be focusing mostly on the intersection of motion planning and formal methods. Of course, there's lots of other work. Our work has also done some work in this area, motion planning with AI, which may be more relevant to you guys, but I think many of the ideas that I'll be talking about in this area are still applicable here and possible to make these connections. Alright, so you can solve this entire problem with sampling-based planning. So we have an overview, here's an overview of some architecture of our system. So let's say, I'll explain these boxes, what they really mean later on. But let's say we just have our low-level planner. And we get some specification that for now, we don't worry about it. We have some specification, and we can really, sorry, I skipped ahead a little bit. We have a specification in linear temporal logic. How many people have heard of linear temporal logic? Okay, a few. Okay, so you imagine your standard Boolean propositional logic. You have a set of propositional variables. You have connectors and or not. And we have temporal operators. Next time some proposition needs to be done, eventually something needs to be valid. Something needs to be always valid, or valid until something else happens, and so on. So that allows us, it's not specific to motion planning, obviously. This is originally proposed as a way to test whether software and hardware behave correctly. So this has some specifications that the system eventually needs to handle some interrupt, for instance, right? If you have an interrupt handler, you want to eventually handle that. So we can describe our formulas as a formula is either proposition, not, or, and then you have the next until eventually. So this is actually a reduced form of linear temporal logic called cosine LTL. It's not the full form, but it still allows you to express many things that we care about in robotics. So eventually, I want Uber to pick me up. Uber has autonomous cars that they want to verify that if somebody places a request for a car, eventually a car will pick you up. Right? Or eventually, I want to visit a number of locations. I don't care about which order, eventually all four needs to be visited. So these are kind of things that are easy to express. This is a little bit more complex, and I'm not going to even try to attempt to translate this into English. It gets complex very quickly, and hard to actually try to go the other direction as well, to go from a natural language specification to linear temporal logic. But that's a separate problem that for now we'll just ignore. So from a specification, you can construct an automaton that basically accepts all the valid traces of propositional assignments. So basically, at time 0, we have one predicate true, at time 1, another predicate is true, and so on. And we basically turn this formula into an automaton at time double exponential. So that looks like bad news. It turns out that many specific types of formulas like this one are very easy to construct an automaton for. So it turns out for many robotics types of specifications, you can construct this automaton in much less than exponential time. Alright, so this automaton will then be used to guide our exploration in a bit. So if we have a formula of this type, in the future visit P1 and then visit P2 or P3. So let's say we have a Mars rover that will collect samples from this rock and then eventually go to the top of these two hills to recharge and get into the sun. I don't care which one. There's some obstacles in the way. First we get this formula, eventually P1 and eventually P2 or P3. It becomes this automaton. Says, well, initially we're here, then P1 becomes true, we reach this state, then eventually P2 or P3 becomes true, and then we have an accepting state. Or we have simultaneously P1 are true, or P1 and P3 is true, and we've done it one step. Okay, so one thing we can do is just generate all kinds of paths, and then use the automaton as a way of keeping track of what state you're in the automaton for a given path. So I can draw a path here that goes from here to P1. And that path would then correspond to being in state 1 over here. And if we follow this path, then basically nothing happens, and then eventually we reach P1. And now we're in this state of P1. And then we wander around some more, and maybe eventually reach P2. And then we reach state 2. So we basically keep track of every trajectory, continuous trajectory, what is the corresponding path in the automaton. That's for every trajectory that we generate, we can keep track of where we are in the automaton. And then once we find the path that is in an accepting state, we say we're done. Okay, so this is kind of like a stab in the dark. We're using a motion planner as this really big hammer to say, let's generate all the trajectories and hope for the best. I hope that at some point we find a path that magically satisfies our complex specification. So the complex specification might be go back and forth between A and B a number of times. The chances that your sampling-based planner will produce such a plan are really, really low. And so generally this is not recommended to go from your specification to your automaton, and using the automaton as a way to monitor what the low-level planner is doing and then hope for the best. And you're putting all the effort in the low-level planner. That's not going to work very well. So instead, what we want to do is construct some abstraction of the environment, and then use that abstraction combined with the specification to construct a feasible high-level plan in the abstraction, and then to say, well, let's use that high-level plan as a guide for the low-level plan. Okay, so to illustrate this, it's best to forget for a moment about the temporal logic specifications and only focus on the abstraction part. So let's say we are in this initial state, so we want to go to a state over here, and we've discretized our world with grid cells. We're just doing a grid search to find a collision-free path. Now, we're planning for a car-like robot, so I will not be able to follow this, but we can use this sort of sequence of cells as sort of a tunnel or funnel for guiding our robot. As you say, well, select your key expansion to be around this red line. And again, so if we do this for a small period of time, we make some progress, then we basically update how much progress we've made from the low-level planner back to the high-level planner. We provide a guide from the high-level to the low-level, then the exploration information is propagated by adjusting the cost of traversing certain grid cells. So we've made lots of progress, we say, well, the cost is very low, we basically got stuck somewhere in terms of dynamics. It's not feasible to move in that direction as the guide suggested, then we increase the cost a little bit. So next time we find a new guide, we may choose something, a different path. Unless we were made a lot of progress, then maybe we choose the same one. So we choose, in this case, we choose a different path, start exploring around that. And we keep repeating this process where we suggest a guide based on what we've learned so far about the environment. So we suggest a high-level guide that is low cost. Use a low-level exploration. Based on how much progress we made, we can adjust the cost of traversing different cells. And repeat this process. We basically have time slicing where we sort of run the low-level planner, update cost, find a new guide, and repeat until eventually we find a path. This is kind of a crazy environment where the large turning radius for our car is very difficult for it to move around, but eventually it does find a path. But this interaction between the high level and the low level is key. That's what allows us to find something that is not just blindly exploring everywhere, it's a guided exploration, but it's not, the high level guide is not dictating completely where the road is going to go. There is this interaction that is very critical. So this is work that our group has been working on for a long time. And I'll try to show that this idea of interaction between high level and low level is not restricted to just this scenario or a scenario where we're looking at linear temporal logic. It actually can be extended to many ways of integrating passive motion. Okay, so let's go back now to the original version where we have this LTL specification. Gets turned into an automaton, and this environment abstraction now to provide this low-level guide. How do we make sure that we are a guide that satisfies both the automaton and is somehow corresponds to the path in the abstraction? Well, the way to do this is we take our automaton, construct it from our specification, and we take our abstraction. Here shown more generally as a graph, but it can really be just a regular grid partition of the space. But it basically, think of these nodes as grid cells, and the edges between them as a neighborhood relationship. And so in a regular grid between 2D, and there's usually four-way neighbors. Right? So in this case, it's just drawn a more general graph, because it doesn't have to be a grid in 2D, or it doesn't have to be. So it can be really anything, really some kind of abstraction. You can also think of these as maybe rooms, and edges correspond to doorways between them. And what we do with these two discrete objects is start the product between them. So what it means is that really it is the states where you are in B1, for instance, in the abstraction, and state Z0 of the automaton. So you can find a path in this product that corresponds to a continuous path of abstraction and a particular run of the automaton. And in this resulting abstraction slash automaton, we can find, again, these accepting states. We can find paths through this graph that will basically guide us from our current state to an accepting state. Right? That will not just contain information about the formula, but also necessarily correspond to a continuous path in the abstraction, which is exactly what we want. Right? So there's a lot of abstraction going on here. There's an abstraction of the environment, and there's a linear temporal logic specification. But in the end, you get something that couples the continuous space with the specification. Right? So you get an abstract high-level plan on how to move around and satisfy the specification. So that is now our guide, right? Because this high-level plan now contains as part of it a continuous sequence of cells or in the environment that we can now pass on to our low-level plan to say, try to follow this high-level plan. Okay, so over here, now instead of having just the abstraction of the environment, we have a product of abstraction and automaton, which provides the guides, and the same idea still applies. We can still say, well, now we have a sequence of cells, let's try to grow our tree to sort of stay within this sequence of cells. And then again, once we've done this exploration for some time, we update our secret, our estimates of how much we've explored, and which will be used in the next iteration then to suggest possibly a different guides, possibly the same one. Right, so we will never get stuck. We can prove that this actually is still probabilistically complete. We will find a path to a trajectory that satisfies the specification if one exists. Okay, so now we can indeed find a solution to this original problem and do the following in any order. We water the plant, turn on the coffee machine, clean everything. This trajectory was found by our planner and it does indeed satisfy all the specifications. So we kind of left out the detailed interaction where you actually flip switches and things like that. Actually manipulate objects. That's sort of a problem in itself. So let's, so this framework where we have this high-level guide and low-level planning extends to many other areas. So more narrowly, we can extend from co-safe to safe and combine it. We can have a three-way product between a safe formula, safety formula, a co-safety specification, describe the task, and the abstraction, and then still do this kind of task and motion planning. We extend this hybrid systems where we have both the discrete part of the low-level space and the continuous part. We can also,
Mark, one question. So why do you do the composition between the automata and the abstraction and not with the probabilistic roadmap, for instance, directly? Is it computational reasons or is it because you need to keep track of the symbols that are mentioned in the LTL specifications? So in principle you could do the composition between the automata that you get from the LTL specification and the probabilistic roadmap, right? But you don't do that. You say you do the composition with an abstraction. So
yes,
why you do that? For computational reasons or because you need to keep track of the truth of these symbols, okay, that are being introduced in the LTL specification?
Both. But yeah, the propositions are over, yeah, that's actually a good point. Because the propositions are assumed to be over regions in space. And these regions are part of the, corresponds to regions in the abstraction. So we have particular regions that they go to P1. P1 is a particular region in the abstraction. So that's one reason that we have the abstraction. It's to say, well, there's all these states. We don't really care where we sample these states, but we have to be in this region somewhere. And we represent the one thing in our abstraction. But we're still generating, the abstraction remains fixed throughout, whereas we are generating the roadmap or the tree as we go along. So it will be difficult to find sort of high-level plans that satisfy the specification, because initially we don't have any states just yet. Initially we are relying only on what we have, the states we have sampled. We cannot sample anything. We cannot generate a candidate solution just yet. So that's where the abstraction will come in. It's just suggest candidates. So it may not be feasible. It may suggest that the rule is made that it's rules collision free, but really when you find out that the dynamic is not feasible or it requires even geometrically different. The high-level guide is, the abstraction can be imperfect. Doesn't need to be conservative or optimistic. It really can be any kind of approximation of the better the approximation is, the more helpful it is, of course. But it's not necessary that the abstraction has to have certain properties.
And if the plan then fails because the abstraction was not sufficiently precise, so how you iterate? How do you change the second iteration from the first one?
Well, that's where the low-level feedback comes in. So go back to this. So we suggest, let's say, the initially say, pick the shortest path. That's what we want. We really have no reason to prefer a longer path. We find the shortest path in our high-level algorithm, and the product with the abstraction says, okay, walk this way through these cells, and you reach an accepting state, and we have a continuous path. It may turn out that if let's say I have a big robot, and I move out the door, it says, okay, move this way first, and then go somewhere in between the row checks. That may be the shortest path. And maybe there's another equally short path, but this is the path that was suggested. It turns out that the robot cannot navigate around the camera, but to actually find out that that's not possible, it needs to invoke the low-level path. Well, let's say this is the initial low-level path, and the low-level plan will try to find the path, and the low-level path around it. It doesn't succeed, but makes some progress, and that exploration information is then used to update with some heuristics for the cost of each cell, the network traversing each cell. So implicitly, we have a graph, weights associated with the abstraction that say this is how much you have to pay to make this transition. Initially, all the costs are the same. As you explore more and more with the low-level planner, you find out that, oh, actually, it looks like I have to pay a lot. It may be possible to reverse, but you never know for sure with a center-based planner. So we just say, well, we keep increasing the cost the more time we spend on traversing that edge. Eventually, this alternative route, maybe going the other way, that's geometrically equally short in the intersection, it looks more attractive than center-based planner might find path that way. But just in the ways just right, so that you preserve this probabilistic completeness and are not too much focus on exploration, not too much focus on exploitation. It's a little bit tricky, but you can show that by doing it just right, you preserve this completeness property. Okay, so we can extend the same idea to other types of systems, other types of specifications. So some of you may think about LTL is not the right way to specify a task. I like PDL. We have been working on extending things in that direction as well. The idea of using a high-level abstraction to suggest candidate plans and having a low-level planner provide feedback to the high-level planner, that's really the key idea. We have this alternation between suggesting plans, high-level plans, finding a low-level plan that might be landed and just makes progress towards it, and using that progress to update the next high-level plan. That's really the key idea. And you can extend this also to partial satisfaction. Initially, in the very beginning, I showed this movie where some obstacles were known, some obstacles were not known. So in some cases, maybe you assume that all doors are open, and the robot should clean all rooms, but doesn't know how to open the door, and it just has to skip some rooms. So you have a partial satisfaction of a formula. Right? So it says, clean all the rooms. Well, rather than say, fail, I cannot clean all the rooms, which you clean as much as possible, and just say, well, I'll just clean whatever I can, and that should be good. That's really partial satisfaction. So far, I've basically shown you a complex version where we have both the complexity of linear temporal logic and the complexity of planning with dynamics. All the examples I've shown for this part of the talk are for car-like dynamics. But in many cases, we really want to push complexity in that direction, and we want to push it in the direction of more degrees of freedom. And that's when you end up with manipulation, where people typically kind of ignore the dynamics. People are really not doing too much with throwing or catching objects. They're manipulating things and trying to move things slowly, this quasi-static way. So if we get rid of dynamics, let's abstract that away and move things more into the dimension of more degrees of freedom, then we can still apply the same kind of approach. So in a few minutes before coffee starts, the coffee's here, and then we can stop because we'll be focused on coffee. I'll talk a little bit about motion uncertainty, which is the last thing that we can extend. extend this to. And now things again change a little bit, the overall architecture remains the same. So let's say that we have a robot that its wheels are slipping, or the floor is slippery, or for various reasons there's some action uncertainty. We start off at some point, if we execute our path in an open loop, we deviate from it, whereas if we have some controller, some policy that helps us, then we can still bound the error and navigate where we need to be. So let's say we still want to execute this trajectory. We need some sort of control policy to help us deal with this. Now, to do this, we still have sort of the same kind of setup, but to generate the abstraction, now we have an abstraction for the dynamics, where we have a bounded market decision process. Have market decision processes been talked about yesterday by any chance? Does anybody know what a markup decision process is? Okay, what do you not do? So DMDP is a special version of MDP where the transition probabilities are within a range rather than a fixed value. We need this range because we're basically just saying we're going to abstract away the transition probabilities from one region to another region, but the dynamics for the transition probabilities for, let's say, a car driving from one cell to another cell, that probability will vary where the car is within that cell. And so we basically have a range of probabilities that describe how successful you can drive a car from one cell to another, depending on where to account for the variability of the position of that car within the cell. So that's technical details. We have a discrete structure that sort of captures the stochastic behavior of the system that says, well, there's many different outcomes of the same action, and we capture kind of the whole range of possible outcomes. So we construct this thing, this sort of extra machinery necessary to construct this abstraction now. But again, we come up with specification, construct the product, and use that as a way to, again, guide the exploration. So some of the components change, the overall architecture remains the same. So that's hopefully the main idea of the interaction between high level and low level this kind of cost. And we can see that that will be useful. And yeah, so this is where I want to stop. And say that we can use these formal methods, combine them with low-level planning, handle all kinds of different versions of this problem, and even handle uncertainty under some kind of conditions. Uncertainty in the environment and uncertainty in action, and really dealt much in sensing uncertainty. So a whole other kind of works, so different kinds of methods. We only dealt with cases where you know part of the environment, part of it is unknown, but you can sense this with 100% accuracy. Your sensing itself is also noisy, then I haven't really come to that sort of separate problem. Okay, so this is a good point to break. So we're right now at part of where we do an overview of OGL to start after the talk. I think there's a half-hour coffee break.